this morning we have studied highly non-adiabatic stars, and we encountered the phenomenon of strange modes and strange mode instabilities being extremely strong instabilities operating on the dynamical timescales, and associated with the strange modes and the strange mode phenomenon is the occurrence of mode crossings and mode interactions. We have then considered or investigated the general property of a mode crossing and the general behavior around mode crossings, and we finally have given a analytically treatable example which has only two modes and where two modes interact and provide a mode crossing which can be treated entirely in terms of analytical computations. This was the double pendulum, and as an example we have found that in fact the well-known and known to everybody the situation or the configuration of the double pendulum might be explained or interpreted in terms of a mode crossing which has unfolded into an avoided crossing. If artificially the coupling constant could be set to a negative value, then we could have obtained an instability band. Now let us go to another example of mode crossings, of multiple mode crossings, and we will consider for this purpose the subdivided organ pipe. Organ pipe was always the analogon to our stellar configuration, and we could draw many parallels between the organ pipe and the stellar configuration. This example will provide or will allow for multiple mode crossings, and the picture we develop from this subdivided organ pipe will be very helpful in the subsequent chapters of this lecture to understand the modal structure of a strange mode unstable and a strange mode affected star. So let us consider the subdivided organ pipe first. What is it? Well, it is an organ pipe. The example, can we take it a little bit smaller? Okay, that's fine. So we have an organ pipe of length L, and we have a diaphragm in this organ pipe which subdivides the organ pipe in two pieces, into a bottom part and an upper part, and this diaphragm lies at a distance L from the bottom of the pipe, and it might be shifted up and down. In the experiment we will shift it from the bottom to the top, and we will see how the acoustic spectrum of the organ pipe will change then. Okay, if this diaphragm is, well, of course the organ pipe satisfied the one-dimensional acoustic wave equation. We have already considered this in detail, and the acoustic wave equation which is valid for this configuration is second derivative with respect to time of the velocity perturbation, the Eulerian velocity perturbation, minus sound squared times the second derivative of the velocity perturbation with respect to the spatial coordinate is 0. Now we have at least two boundary conditions at the bottom and the top of the pipe. If we have rigid boundaries, or if the organ pipe is closed on both sides, then we have to require that the velocity perturbation has to be 0 both at the bottom and the top of the pipe. That means at x equal to 0 and x equal to capital L. If the diaphragm perfectly decouples the upper and the bottom part of the pipe, then we have to apply this boundary condition also at the diaphragm. If it's a perfect decoupling of the two parts, then we have to imply these boundary conditions for the bottom part also at x equal to L, and for the upper part at x equal capital L. Of course, the two previous boundary conditions still have to be satisfied. So we generate two spectra in principle, one associated with the bottom part of the pipe and one with the upper part, and this is generated by requiring the boundary condition at x equal to 0 and x equal to L at the position of the diaphragm, and for the upper part at the position of the diaphragm and at the upper end of the pipe. Okay, so these two parts, these two spectra, which are generated by imposing the boundary conditions in the way given here, they are, if the diaphragm is perfect, they are independent of each other. So the two parts of the pipe cannot communicate. The solution of the wave equation in any case is given by an exponential I omega t plus ikx. So we have an exponential behavior both with respect to the time behavior and the spatial dependence. The dispersion relation which we obtain from this form of the solution, if we insert it into the one-dimensional wave equation, is identical for the upper and the lower part, and it's given by minus omega squared, eigenfrequency squared, plus c sound squared times wave number squared is 0. Now we impose, with this dispersion relation valid in both parts of the pipe, we impose boundary conditions for the bottom part. These read in the following. So this is the form of the perturbation. The velocity perturbation is a superposition of a wave which goes from bottom to top and from top to bottom. So at x equal to 0, we derive 0 has to be c1 plus c2, and at x equal small l we have 0 is c1 times e to ikl plus c2 e to minus ikl. Replacing c1 by c2, and we are left ultimately with 0 is e to ikl minus e to minus ikl, and in the end we have the following relation for, or the following equation determining the wave number k. E to ikl is 1, and 1 might be written in the complex plane as e to I times 2 pi n, where n counts the number or the order of the overtone. N equals 0 is the fundamental, n equals 1 the first overtone, and so on. So k is given by the order of the mode divided by the length of the bottom part of the pipe, and omega squared is then given according to the dispersion relation simply by sound speed squared times pi squared times the order squared of the mode divided by the length or the distance between the bottom of the pipe and the position of the diaphragm. Well, let's consider now the spectrum of the upper part. Well, there we have to impose the boundary condition at the position of the diaphragm. So velocity is 0 there, which is given by c1 times e to ikl plus c1 to e to minus ikl, and the boundary conditions at the top of the pipe, or of the top of the upper part, has to be imposed at the position capital L. This gives two boundary conditions, and this equation leads to a linear homogeneous equation for C1 and C2, may be written as a matrix A times the vector C1 C2. This has to be 0, and the necessary condition for this to have a non-trivial solution is that the determinant of the matrix A has to be 0. The determinant of this matrix is simply these two elements minus these two, the product of these two elements. So the determinant is given by e to ik, difference between the position of the diaphragm and the length of the pipe, minus e to ik, and again the difference between the position of the top of the pipe and the position of the diaphragm. This again leads to a similar equation as for the bottom part. That should be expected that the relations are similar, but e to ik L difference L small l minus capital L is 1. This is again in complex analysis given by e to I 2pn times the number or the order of the mode now for the upper part. This is a different n from before, so this is the order of the modes of the upper part, and so k, the wave numbers for the upper part of the pipe, of the top part of the pipe, is given by pi times the number, the order of the mode times the difference of the position of the diaphragm and the length of the pipe. Accordingly, with the dispersion relation, we end up with omega squared is c sound squared divided by L minus capital L squared times essentially the order of the mode of the upper mode squared. So these are the two spectra of the bottom part and the top part. U means upper part and B, subscript B, means the bottom part of our pipe. Okay, so we have two dispersion relations, the bottom part and the upper part, and the dispersion relations are given by omega squared minus c sound squared over L squared times pi squared times the number, the order of the mode, respectively, for the upper and the bottom part. Well, these are separate dispersion relations once the diaphragm is perfect and the modes do not have the sound waves of the upper and bottom part do not have the chance to interact with each other. In general, however, the diaphragm is not perfect and we will have a coupling between the upper and the bottom part of the pipe. So to account for the imperfectness of the diaphragm, we write the dispersion relation of the complete system containing both the upper and the bottom part as a product of the dispersion relation for upper and bottom part being no longer zero but being given by a coupling function epsilon, which may depend also on the frequency omega. We will assume in the following that epsilon is bigger than zero and that epsilon is a real quantity. Just for simplicity, we could also assume epsilon complex or negative. If we want to calculate this epsilon, we have to go in a more sophisticated way. Well, but it could be done. I will not do it because it is easy and it's straightforward to do it, but it becomes the mathematics in the algebra explodes. So you will have to deal with many terms, and actually for the physical insight it does not provide a big advantage. And so I just sketch a little bit in a very rough way what could be done, or how a more sophisticated treatment of this system might be done. Well, we can, in a sophisticated treatment, we may regard the diaphragm as a thin slice with high sound speed. We just take a thin slice which has a high sound speed compared to the sound speed within the upper and bottom part of our organ pipe. Well, the acoustic wave equation is similarly valid in this within this slice as in the pipe as well. So there is no change concerning the wave equation that needs to be considered. It's only that the sound speed has a different value within this slice than outside in the organ pipe. Well, the boundary conditions that have to be imposed are the same as before. The velocity perturbations have to be 0 at the bottom and the top of the pipe, and at the boundaries of the slice. However, just we have to impose continuity equations, because the wave equation is of second order with respect to the differentiation with respect to the spatial coordinate. In order to allow for a second order derivative, of course, the first derivative and the function v tilde itself have to be continuous. So at the boundaries, at the edges of the slice, at the interfaces of the slice, the velocity perturbation and its derivative with respect to x have to be continuous. And these continuity equations then, well, the continuity conditions will then allow for a continuous connection of the two different parts of the pipe. And finally, what you end up with is an explicit form of the coupling constant or the coupling function epsilon. Okay, well, once you go through the analysis of this problem, you will find similarities to a well-known problem, a problem which is well known to you. It is the problem of the tunnel effect at a potential barrier. So in that case, you also adopt continuity conditions at the edges of the potential barrier, and what you will find is some kind of tunneling, now not of quantum mechanic waves, but of acoustic waves through an acoustic barrier which is caused by a slice with high sound speed. So the mathematical problem is very similar to the effect of the tunnel effect at a potential barrier in quantum mechanics, and the final result then is some kind of the probability for tunneling, or here it is not the probability for tunneling, but the function which describes the coupling of the top and the bottom part of our organ pipe. Okay, the final result is epsilon as a function of omega, which is bigger than 0 and is real. Well, since epsilon is bigger than 0, these mode crossings are expected, or any mode crossing is expected to unfold into an avoided crossing. No instabilities and no instability bubbles are generated in this way. Okay, so well, we will now do an experiment. We change the position of the diaphragm from bottom to top. So we change the length of the bottom part from 0 to capital L, and at the same time we reduce the length of the top part of the pipe from capital L to 0. So we have, and we consider now what the frequencies, how the frequencies of the top and bottom part vary with the position of our diaphragm. We will do it not mathematically, not in explicit doing explicit mathematical computations. We do it in a more intuitive way, an intuitive graphical way. We'll see in a moment how we shall proceed. So the experiment will be shift diaphragm from bottom to top, and assume that the modes couple with a finite epsilon, so the diaphragm is not perfect. Okay, so what we have for the bottom part, we have a 1 over L dependence of the frequencies. So once the diaphragm is at the bottom, the frequency of the bottom part are infinite. So they tend to infinity if we decrease the length, the position of the diaphragm to 0. They are at infinity, whereas the frequencies of the upper part are regularly spaced, and they have a fundamental frequency and accumulate at infinity. Now, well, once we shift it now from the position from the bottom to top, then the frequencies of the bottom part will decrease like 1 over L, and finally once we arrive at L equal capital L, we have a we have a spectrum having a fundamental, first overtone, and so on. What happens to the upper part? Well, if we change from capital L from L equals 0 to capital L to the top, well, then the frequencies which have been at L equals 0 been finite and regularly spaced will diverge like 1 over L minus capital L once we approach the top part of the once we approach the top of the pipe, and the length of the upper part goes to 0. So then the frequencies of the upper part of the pipe will diverge. So these ones decrease with L, the other ones increase with L. So it is inevitable that these modes will cross. So here again omega, and here is we plot omega against the position of the diaphragm. Here is capital L and here is 0. So for the bottom part we have infinite frequencies here, and they decrease once we approach L. So this is the fundamental, first overtone, second, and so on. They diverge for the position small l going to 0. The other just do the opposite. They start here, the upper part starts here, fundamental, first, second overtone, and it increases and diverges once we approach capital L. So we get this picture, and we inevitably get multiple mode crossings between the upper and bottom parts of our pipe. So we have generated an infinite set of mode crossings which do not stay as they are. This would be the picture if the two parts of the pipe would be completely independent and the diaphragm would be perfect. Actually, this picture must be symmetric with respect to L capital L halves, so we have a symmetric picture with respect to this line, which is L half. Okay? Everybody agrees or objections against this picture? Okay. Now we know if the diaphragm is not perfect and epsilon is bigger than 0, then these crossings cannot stay as they are, but they have to unfold according to the avoided crossing scheme. So let's take one of these crossings, for instance here. This is the crossing. Avoided crossing means that this mode is continuously connected to that one, and this one is continuously connected to that one. The same happens here, and we get, as a result, we get an avoided crossing here. So this gives the impression of a staircase of modes, and it gives a rather bewildering and at first sight not understandable pattern of the crossing or of the run of the modes as a function of position of the diaphragm. I've done this here a little bit more in detail and more careful. So this here is the modal diagram which we expect. Well, the black lines are the decoupled, the original modes, the bottom modes. This is a set of bottom modes decreasing with increasing L. These ones are the spectrum of the modes in the upper part of the organ pipe, and the crossings here have unfolded according to the avoided crossing scheme. and so this gives this wave-like appearance for the run of the various modes as a function of position of the diaphragm. If we artificially would be able to have a negative coupling or have negative values of epsilon, then we would have a coupling in the green scheme. So then these modes would be connected, and we have a common real part in between these couplings. The same would be here, but at the same time we would have a bubble of instability, and the imaginary part then would no longer be zero. So we may have, if the system would allow both for negative and positive coupling, then we would have avoided crossings or instability bands within the same system. It depends on the sign of the coupling whether we get instability bands or avoided crossings. Maybe we can use, or we keep this picture in mind without the negative coupling, without the instability bubbles. Just keep this picture in mind. Maybe we can make use of it later on once we consider the modal diagram of a massive star. So I'll come back to this point, and of course if we find a massive star which shows a modal diagram which is similar to that, then we might ask, well, there must be in this star must be a diaphragm, like in our organ pipe. Question is, where is this diaphragm and what makes this diaphragm? And if this is true, then we can, keeping in mind the simple picture of the subdivided organ pipe, we may get a feeling and an interpretation of the modal diagram of a massive star. I have done this in detail because you actually can use it, and you can transfer this picture to the modal diagram of a massive star and interpret the diagram in using this simple picture of the subdivided organ pipe. Well, the advantage of this picture is you can draw the modal, the run of the modes without reference to any complicated mathematics. It's just the coupling scheme which you need to know, and the run of two sets of modes which might be caused or might be generated by having a acoustic diaphragm in your star, which in the course of evolution may shift from bottom to top of the organ pipe. Okay? Questions?
So how do we determine what instability will be? I just saying that L24 and the bottom piece.
Yes. You mean here?
How do we determine that there won't be any problem instability in this without?
Well, the red curves assume that epsilon is positive, and this is artificially assuming or assuming that we have a negative epsilon. Then we would unfold it according to that scheme. Actually, epsilon is positive for the organ pipe. It's just as a it's an academic question. How would the diagram look like if we would have the possibility to have negative coupling? How would the picture look like? Actually, it will not look like, because we know epsilon is positive, so we will only have avoided crossings. Sequence of infinitely many avoided crossings. So it's the hypothesis that we might have epsilon smaller than 0. Okay? Well, the occurrence of mode coupling and the occurrence of instability bubbles is not restricted to stars and strange mode. They occur also in many ways in fluid mechanics, And one of the examples, one of the nicest examples I know of, is the stability problem of plane Couette flow. What is plane Couette flow? Plane Couette flow is the flow between two planes which are sheared along each other. In a viscous treatment, then a shear layer will develop where the velocities are at the boundaries are equal to the velocities equal to the velocities of the boundaries, and this shear flow is generated simply by the motion of the two planes shearing along each other. So the surfaces are, these two surfaces are shearing and generating a shear flow between the two confining planes. Well, for this flow it's found that turbulence sets in around a Reynolds number of thousands, and if we do a stability analysis, then we will find that actually if the theory is incompressible, then we will find that laminar flow is always stable, and people therefore think that there is a subcritical transition to turbulence. Well, we can also consider compressible perturbations, and if we do that, then we find in fact instabilities in the supersonic regime, and the critical Reynolds numbers are of the order of 100, and these instabilities in the supersonic regime are produced by resonances or mode crossings among sound waves. And I will show you the picture. So we have a nice example in that case for the instability bubble picture, or the instability bubble picture, which is usually not seen in these very simple cases. In the double organ pipe, in the subdivided organ pipe, we always have avoided crossing, and also for the double pendulum we have only avoided crossings. Here we have the case where we have crossings of modes which have unfolded into bubbles of instabilities. So what is going on there? What is plotted here is the pattern speed of waves which have a character of standing waves between perpendicular to the planes, but which have the character of waves traveling along or in the flow direction in x direction. So these are modes. These are a set of discrete modes. This mode goes in the positive x direction, and those with negative values go in the negative x direction. So we have two sets of modes with standing character perpendicular to the planes and with traveling character along the parallel to the planes, and we have two types of waves going in opposite direction. The system should be symmetric with respect to plus and minus x. These are the modes, and once we turn on now our flow, and the flow speed is parameterized or given here in terms of the Mach number measured at the edge of the flow. So the flow speed is 0 here, and it increases, and the flow speed is measured in units of the sound speed. So we plot it here as a function of the Mach number. So what happens here is these modes are affected by the flow, that they are traveling parallel or anti-parallel to the flow. So they are affected and they become distorted, and they become distorted in a way such that they cross each other. So this is a plot where where we succeeded in decoupling these two sets of modes. So they are here neutrally stable, and they're decoupled. We could suppress the coupling between these, but once we turn on now the full system of equations, then we will see how these mode crossings have decoupled. So it now looks like the real part looks like kitchen tiles here. They are merging around these crossings. Then they form the typical instability bubble coupling, and they decouple again here. So we have lots of overlapping resonances and couplings in this kitchen tile profile. The imaginary parts look like these. These are the bubbles which correspond to all these parts here. So we have a superposition of many bubbles, and this is typical instability bubble result of the coupling or of the crossing of two modes having unfolded, this time not according to the avoided crossing scheme, but according to the instability band scheme. Actually, we have also some avoided crossings here, which are the outermost crossings which have unfolded into avoided crossings. So we have also a sequence of avoided crossings here, but the main part of the crossings have unfolded according to the instability bubble scheme. So just to show you a very clean case of coupling, or very clean case of coupling which has unfolded into the instability band scheme. If you remember the coupling which was found in the hydrogen deficient carbon star, it was simply a sequence which is similar to one of these sequences found here. So it's one instability bubble behind the next one. Okay, now, well, we have seen fluid mechanics. In fluid mechanics we have many examples, compressible Couette flow, examples for mode coupling and instabilities associated with mode crossings and mode couplings. We have the hydrogen deficient carbon stars, and we have the Wolf-Rayet stars, which may be regarded as one-sided instability bands. So what we see is the beginning of a coupling scheme. We don't see the end of the instability bubble, we see just the onset of the instability. Well, this scheme, the general coupling scheme, may be used to decompose the system, or to decompose the modal diagrams into the constituent modes and reduce the complexity of spectra. It may also be used to find missing modes, and occasionally these coupling schemes may contribute to a better understanding of the instability mechanism. Now, well, we are dealing with strange modes, and let's now come back to the study of strange modes and non-adiabatic stars. Well, the Wolf-Rayet stars and the hydrogen deficient carbon stars are by no means the only stars where strange modes and associated instabilities are found. If you go to massive stars with high luminosity to mass ratios, you inevitably see strange modes and associated instabilities. So for instance, if we go to massive stars, you find even the boring zero-H main sequence stars exhibit strange mode instabilities if you go to high enough luminosities. So strange mode instabilities are found even for zero-H main sequence stars with masses above 80 solar masses. There are various strange modes, and the NAR approximation is, at least qualitatively, not too bad. Quantitatively, it's less satisfactory. And what has been done in the early years of discovery of strange modes instabilities in massive stars, instability has been considered along evolutionary tracks, and in fact, if the masses are high enough, then we found a variety of strange mode and strange mode instabilities, and we will look at these instabilities in detail in the following. Okay, so this is the result of a non-adiabatic stability analysis along the zero-H main sequence. L is equal to 0, so we consider spherically symmetric perturbations, and once we do the non-adiabatic analysis carefully enough, we see there are many modes crossing each other. There is the strange mode phenomenon, and there are crossings associated with high growth rates, with sigma I being negative, and here this is the mode seen here. This is the S1U. You have sigma I of the order of minus 0.2 or minus 0.3. So these stars become, these zero-age main sequence stars become strange mode unstable once the mass lies above around 80 solar masses. So even the boring zero-age main sequence stars exhibit strange mode instabilities if the mass is high enough, if the luminosity, of course, increases also with mass, and the luminosity to mass ratio increases once the mass increases. Luminosity goes roughly proportional to m cubed. That means that the luminosity to mass ratio goes with m squared. So this is the origin of strange modes this is the situation with strange modes in ordinary main sequence stars. Well, concerning the NAR approximation, well, it seems that there are strange modes also in the NAR approximation, but once we compare the diagrams, the quantitative agreement is not that good. That means the conditions for the application of that approximations are not satisfied to the same degree as it's satisfied for the Wolf-Rayet stars, for instance. Now let's look what has been done concerning the investigation of the stability along evolutionary tracks. Here we have evolutionary tracks of massive stars. 20 solar mass, initial mass, of course, corresponds to 20 solar mass, initial mass 30, 40, 45, and we end up with 80 solar masses for the most massive stars. Okay, now we'll consider in a moment how does the modal diagram along such a evolutionary track look like, and we will start with the 20 solar mass object. 20 solar mass object and spherically symmetric perturbations. So this is the result, the modal diagram for spherically symmetric perturbations starting at the main sequence. This is the contraction phase, therefore we have this loop here, and this is the result of the linear non-adiabatic stability analysis. Whenever we have thick dots, the modes are unstable. Well, there is no indication, no real indication that there is some mode crossing or mode coupling present for this star, but it is still unstable, or it's unstable around effective temperature between log T 4.5 or 4.4. Actually, if we compare it to one of the classical pulsators, this is the 20 solar mass object is close to the beta Cepheid regime, so this actually might be interpreted as the kappa mechanism due to the heavy element abundances. So this instability strip enters the beta Cepheid regime. Now we increase the mass, and we end up, the next track we consider is the track of the 60 solar mass object with perturbation with respect to spherical perturbations. Now we see strange mode phenomena to appear. Well, there seems to be a lot of avoided crossings appearing here. There are modes crossing here in this regime. There seems to be a sequence of avoided crossings here. And, well, so we have the classical picture of strange mode instability in this diagram. Once we consider the growth rates, well, the growth rates are also in the dynamical regime, then we see, well, it seems to be that the growth rate has a first maximum here, a second maximum here, and a third maximum here. In a phenomenological way, one could associate these three maxima with the maxima of the opacity. Okay, and therefore These strange modes are usually, or are by some authors, are called the iron or the heavy element strange modes. This is the helium strange mode instability, and this is the hydrogen helium instability. So it's in a phenomenological way without reference to any physical explanation or physical process. They may be just grouped or classified as iron, helium and hydrogen helium strange modes. But it's strange mode instability, and the growth rates are pretty high. It's of the order of minus 0.1 or 0.15 even for this case. Okay, well, let's go back to this picture here, to the real parts. Well, what does this, if we ignore the low temperature part, what does this picture remind you? Or if you see this picture, what do you get in mind? Compared to something which we have discussed just a few minutes ago. It looks like, at least qualitatively, it looks like the subdivided, the pattern which is found for the subdivided organ pipe. So one might try, well, this is a fully non-adiabatic treatment. Let's try an adiabatic treatment of this part of the diagram. Let's see what we find. Well, adiabatic treatment, we have only neutrally stable modes. And how does the adiabatic treatment, at least for the high temperature part, look like? So, same stellar models. Now we adopt the adiabatic approximation. Well, the helium and hydrogen strange modes are gone. They obviously do not have an adiabatic counterpart, but at least qualitatively, the pattern of the frequencies seems to resemble the pattern of the full non-adiabatic problem, and it still resembles that of the subdivided organ pipe. So what might have happened, or if the picture of the subdivided organ pipe is wrong or is applicable, then this run of these modes might be caused by a kind of diaphragm in the stellar envelope. The question is, which is the diaphragm, or where is the diaphragm in the stellar envelope? Well, to see this, we have plotted in the next plot here the run of the adiabatic sound speed as a function of radius for 3 different models of the previous diagram. And what we see, the sound speed is by no means a monotonic function, but it has a peak here. There is a peak or a maximum in the sound speed once we consider it for 3 models. Okay, this peak in the sound speed in effect may take the role of a diaphragm with high sound speed which decouples 2 parts of the stellar envelope. This peak in the sound speed is nothing but a way to decouple and to reflect sound waves at a certain position and to decouple 2 different parts of the stellar envelope. Now, once the star evolves, the relative position of this diaphragm, of this maximum of the sound speed, changes, and therefore, so to say, the length of the pipe changes. The length of the two acoustic cavities which are separated by this maximum changes. You see it from here to here. Well, this is the position of the diaphragm. Here the difference is much smaller than here between this maximum and the outer boundary. So the frequency which is associated with this part will decrease because the sound speed, or the sound travel time between these 2 positions becomes longer, and therefore 1 over the sound travel time the period becomes smaller. So if we plot the sound travel time between this maximum position and the outer boundary as a function of the model, then we obtain, or we should roughly get, the run of the frequency of the associated spectrum. I've done this. Well, this is the dashed line in this diagram, and we see the dashed line marks approximately the run of the mode which might have given rise to these sequences of avoided crossings. So what we have here and how we can interpret the modal diagram in this case for the massive stars is the maximum in the sound speed has decoupled or has split the star in two acoustic cavities, and the change of the position of this diaphragm will lead to a different behavior of the modes, a different run of the modes with the position of the diaphragm. One of the modes, like the organ pipe, one set of the modes increases because the acoustic cavity shrinks by change of position. The other cavity expands due to the shift of the diaphragm, and so one set of modes increases with evolution and the other set of the modes decreases with evolution. This gives rise to mode crossings which have unfolded into avoided crossings. So the naive and simple picture of the subdivided organ pipe helps us to understand what happens here in the massive star. Or going back then again to the original diagram, here it's even more obvious how these two sets of modes interact, the sets of modes going up there and going down here. So we have two acoustic cavities which are separated by a diaphragm, and the position of the diaphragm shifts such that the frequency of one set of modes increases and the frequencies of the other set decreases, giving rise to crossings, and these crossings have unfolded into avoided crossings. Okay, that is an example how very simple models which can be generated without calculating anything. So this subdivided organ pipe model you can describe and graphically illustrate without having to calculate anything, and the transfer from this to the modal diagram observed or calculated for massive stars will give you a hint how these complicated modal diagrams are generated. Questions? Okay, now let's proceed further. Now let's have a look what happens if we now also allow for non-radial perturbations for models of the 60 solar mass object. Well, you see essentially the same picture. The low harmonic degrees lead to essentially a similar picture, but if you consider the growth rates of the iron opacity strange modes seem to have decreased, whereas the helium strange mode instabilities may have even increased in strength or have at least been unaffected. Okay, let's increase the harmonic degree even more to L equals to 10. Then you see that the iron strange mode instabilities have disappeared, whereas the helium strange modes are still there or even stronger. If we go to L equals 100, then the helium hydrogen strange modes are still there, are very strong, and they even extend towards the higher temperatures which have been occupied before by the iron strange modes. Okay, so once we insert the result now in our Hertzsprung-Russell diagram, we find the following result. We go back to the Hertzsprung-Russell diagram of the evolutionary tracks. That's here. And we denote those parts of the evolutionary tracks on which the models are unstable with a full line, and the parts of the evolutionary track which are stable, where no strange mode, no instabilities were found with the dotted lines. We find that there is a small range in temperatures which is unstable for low masses. This range of models extends and goes even to the main sequence. So it even hits the main sequence. The very thick lines, by the way, correspond to extremely strong instabilities. So whenever we have a very thick line, then the instability exceeds a certain threshold. So for masses above 60 solar masses, we essentially have instability along the entire evolutionary track. Well, the dashed lines appearing here in this diagram is the so-called Humphreys-Davidson limit. It comes from observation and denotes a region in the Hertzsprung-Russell diagram where no stable, no non-variable star is found. So above this Humphreys-Davidson limit, above this dashed line, we do not have static hydrostatic stars, we do not have non-variable stars. So this part of the Hertzsprung-Russell diagram seems to be forbidden for hydrostatic or stationary stars. And well, this region is covered by the iron strange modes, and this domain is covered by the helium and hydrogen strange modes. You already see here that the bottom of this Humphreys-Davidson limit approximately is compatible with the stability limit, which we derive here. This is the 50 solar mass star is the track of the 50 solar mass star is around coincides roughly with the bottom part of the Humphreys-Davidson limit. All the tracks above are stable. So this is expected to depend, of course, the iron strange modes on the iron opacity. So if we go to a study with low metallicity, we expect this part of the stability diagram to be affected. In fact, this is the case. So if we reduce the metallicity, the chemical composition, then we end up with the following Hertzsprung-Russell diagram. Full lines are unstable branches, dotted lines are stable branches, and we see anything to the left of the Humphreys-Davidson limit, which is covered by the iron strange mode, has now become stable. That's because the third opacity peak due to iron group elements is missing. But remarkable, the onset of instability for the helium and later on for the hydrogen instability coincides with the Humphreys-Davidson limit. So some people, including myself, have claimed that the instability limit we derive has something to do with the Humphreys-Davidson limit, or might be possibly an explanation of the Humphreys-Davidson limit, because the instabilities, the strange mode instabilities, which are independent of the metallicity, of the chemical composition of the star, which are defined by helium and hydrogen strange modes, they essentially cover the domain which is found to be empty with respect to stable, to stationary, non-variable stars. Okay, so these are pretty robust, these instabilities. They do not have an adiabatic counterpart. They are not affected by metallicity or chemical composition, because of course helium and hydrogen is the composition of hydrogen and helium is essentially fixed by primordial abundances. Okay, in a little bit different representation, here in red the unstable domain. Here it hits the 0H main sequence. Here we go into the beta Cepheid regime, And this part is not found once we reduce the metallicity, and the bottom of this line here is defined by, or coincides with approximately with the Humphreys-Davidson limit. Well, for small metallicity, we still have a coincidence of the instability domain and the left branch of the Humphreys-Davidson limit. Down here it fits not that nice. Nevertheless, it seems, or we suspect there is some relation to the Humphreys-Davidson limit. Okay. Now let us summarize the properties of the various iron, hydrogen, and helium strange modes. Well, I haven't covered the point that the treatment of convection might be crucial in some cases to the results of the instability or the stability calculations. The iron strange modes are sensitive to the treatment of convection. The helium and hydrogen strange modes are insensitive. Well, dependence on metallicity, of course, the hydrogen, helium are insensitive. Dependence on metallicity, of course, iron strange modes depend on metallicity. Well, the harmonic degree for which these modes exist is L smaller than 10 for the iron strange modes, and L smaller than 500 for the helium strange modes. The maximum growth rate is found for the iron strange mode at spherical symmetric perturbation, and around L equals 100 for the hydrogen strange modes. Well, for the hydrogen and helium strange modes, the kappa mechanism is not responsible. These are strange modes. For the iron strange modes, partially we have the kappa mechanism, but there are also strange modes instability responsible for the instability. Temperature range, of course, for the hydrogen and helium strange modes, log T is smaller than 4.3, and for the iron strange modes, the log TF is bigger than 4.3. We have found the iron strange modes might have a stable adiabatic counterpart, whereas this is not the case for the helium ones, and the helium strange modes have an NAR counterpart, and the iron strange is partially yes. Okay, this is a summary of the strange modes appearing in massive stars. Well, finally, I would like to comment a little bit on a model for strange mode instabilities. So far we have just provided some conditions, some necessary conditions, which are found once we calculate strange mode instabilities. And one of these conditions for occurrence is that luminosity to mass ratio is bigger than 10 to 3, and that the ratio of thermal to dynamical timescales for a large fraction of the envelope should be smaller than unity. However, these conditions do not provide a simple intuitive model. Well, I'm not sure whether I will be able to provide or to present you now a simple enough model for strange modes, but these conditions are certainly not a direct simple model for do not provide a simple model for strange mode instability. So, well, let's summarize what we know about the occurrence of strange modes before we go to discuss a simple model for the strange mode instability. So, luminosity to mass ratio bigger than 10 to 3, short thermal timescales means radiation pressure is dominant. The strange modes occur both for radial and non-radial geometry, so geometry itself is not essential for this process. Well, they operate on dynamical timescales, so even the growth rate is dynamical. they do exist in the NAR approximation, and this may raise the question whether they are of mechanical origin. They certainly cannot be of thermal origin because they exist in the NAR approximation, which means they exist without heat capacity. Okay, so for a model we can adopt the following properties. Well, geometry is not essential, so we take the simplest geometry we can think of. This is plane geometry. Well, obviously also the consideration of the gravitational potential is not essential, so we adopt Cowling's approximation. Perturbation of the potential is neglected. Then we know the instabilities occur in the NAR approximation. That means we can assume that luminosity perturbation vanishes. Well, if they exist in NAR approximation, the luminosity perturbation is not essential, and we can assume that the luminosity perturbation is zero. Well, then we found that in the configuration or in the situations when the strange modes appear, the contribution of gas pressure is small. That means the ratio of gas pressure to total pressure is close to zero, or we can consider the limit of negligible gas pressure, limit of beta going to zero. Okay, so what we are to justify it here, again, the ratio of thermal to dynamical timescale. It's small for the 24 solar mass object, and it's big for the 60 solar mass object. We have seen and discussed this diagram before. And the other diagram is the ratio of gas pressure to total pressure for the 60 solar mass object. The contribution of gas pressure is always above 10%, whereas for the 24 solar mass object it falls below 10%. Okay, so let us construct now a model for strange mode instabilities based on these simplifying approximations. Well, we have of course we have to do correctly the mechanical equations. We cannot apply any approximation to them, and the first equation which we need to consider is mass conservation in the Eulerian picture. That means the derivative of time, the derivative with respect to time of the Eulerian density perturbation is given by is given essentially by the divergence here in the one-dimensional model by d by dx of rho naught times the perturbation, Eulerian perturbation of the velocity. Well, the momentum conservation equation is, we have discussed similar problems for the organ pipe already, is given by rho naught times the derivative or the Eulerian derivative of the Eulerian perturbation of the velocity, which is equal to the gradient of the pressure perturbation plus gravity times the density perturbation. Well, if we combine these two equations, we end up with the one-dimensional acoustic wave equation. We have seen this several times, and now to close this system we have to apply, or we have to adopt, a relation between pressure and density perturbation. Usually in the common adiabatic approach we assume that pressure is a function of density only. This means that the perturbation of pressure is given by sound speed squared times the density perturbation, and what that means physically is that concerning if you're considering a wave with a wave representing the pressure perturbation and a wave representing density perturbation, that these waves are in phase, because pressure perturbation is proportional to density perturbation. There is no phase lag between pressure and density perturbations. Okay. Well, once we adopt the NAR approximation, this, of course, if we apply this relation of this form to the mechanics, to the acoustic wave equation, we will not get instabilities. It's simply an adiabatic. It will be an adiabatic system, and what we need to generate these instabilities is a deviation from adiabaticity. Okay, so what shall we do instead? We adopt first the NAR approximation. The energy equation is satisfied with vanishing luminosity perturbation. This has been seen already. We have already adopted this. And then the only relation which can provide a relation between the pressure and density perturbation is then provided by the remaining equation, which is the equation for energy transport. The energy transport equation is here written as a relation between the gradient of the radiation pressure and the luminosity. So gradient of radiation pressure is minus opacity times density times luminosity over 4 pi c r squared. Now let's perturb this quantity, this equation. What are we left with? Linearization of this would result in, well, on the left hand side we are left with the gradient of the perturbation of the radiation pressure. On the right hand side we have to perturb kappa times rho. This gives kappa sub rho. It's the derivative of kappa with respect to density, plus the perturbation of density gives the 1 rho Eulerian perturbation of density over the stationary value. And we have to take into account that kappa also depends on the temperature or alternatively on the radiation pressure. So we have kappa sub p rad times the perturbation of the radiation pressure relative to its stationary value. We are in the Eulerian picture, so R is the independent variable, no perturbation required, and L is assumed to be constant. Now, now we consider, in addition to the previous assumption, we consider the limit of high wave numbers. That means if we assume, or if we do a local analysis, then the gradient goes with k times the gradient in the high wave number local analysis is proportional to wave number times the perturbation of p rad. This is to be compared to this term. Now if k is large, then we may neglect this term with respect to the gradient. If we consider high wave numbers, then and which means we are assuming perturbations of the following form: x I k r, and k is assumed to be big than dp rad by dr is ik times p rad tilde, and we have to compare this term with this term. This means for high wave numbers we can neglect this term with respect to the gradient. So we are left with the final result. The derivative of the perturbation of the radiation pressure is essentially given apart from the stationary value by kappa sub rho plus 1 times the density perturbation. Well, if we now assume the limit that gas pressure goes to 0, then the radiation pressure is equal, or in this limit the radiation pressure becomes equal to the total pressure. So we can drop the index rad here, and we have dp by dx, dp tilde by dx is 1 over rho times dp by dx times kappa sub rho plus 1 times the density perturbation. Now, what does it mean concerning the phase difference between the pressure and the density. If we have a pressure, the dependence of pressure like a wave x IKR, what does it mean? Well, are pressure and density perturbation in phase due to the, well, if you take it in a real representation, cosine KR for the pressure. Of course, if we differentiate the cosine once, then we have a phase lag of pi halves. Okay, so what that introduces in the pressure density relation, it introduces a phase lag between the pressure perturbation and the density perturbation. Okay, so in the limit of dominant radiation pressure, we have this relation finally for proportional to c squared times rho tilde. We insert this relation into the acoustic wave equation. Well, minus the first derivative of the quantity gravity kappa sub rho times the density, the Eulerian density perturbation. Now, for plane waves and a local analysis, we write rho tilde as an exponent by the derivative with respect to x gives an ik at this position and gives a minus omega squared for the second time derivative of the density perturbation. And we are left with omega squared is minus ik g gravity times once we would want to take, once we consider k to be a real quantity, omega squared or omega is always a complex function, and it's always complex, and we always have instability. So this, here we arrive at the result that the origin of strange mode instability. Remarkable is that this dispersion relation is usually that of gravity waves. So omega squared being proportional to the wave number is typical for gravity waves, but we are dealing with sound waves, with strange sound waves. So these strange sound waves seem to behave entropy gradient of a gravity wave. You have no gravity waves. This is a sound wave where kappa sub rho is responsible for a non-zero kappa sub rho is responsible for instability. Moreover, you see, it does not depend on the sign of kappa sub rho whether we have instability. Must not be zero for an instability, otherwise it is irrelevant whether the sign of kappa sub rho is positive or negative. And we find a situation where kappa sub rho is responsible, non-zero kappa sub rho is relevant for instability, but kappa sub t is completely irrelevant. This is in the kappa mechanism instability. Okay, now finally, well, the question is, can we test whether this dispersion relation plays a role or not? Well, we have seen it does not depend on the sign of kappa sub rho, but it depends on the fact whether kappa sub rho is 0 or not. Do we have situations where the derivative of kappa with respect to density is 0 in a star? Rho is 0. Well, there is one source of opacity which implies a constant opacity, constant with respect to temperature. Enough star, then we will end up with electron scattering. This is constant, and electron scattering has kappa sub rho equal to 0. Now the problem is, even if the star is hot enough, well, if it includes, or if the chemical composition includes a finite heavy element or if we assume a star having no metallicity, then if the star is hot enough, helium and hydrogen are completely ionized and do not contribute to the opacity, and only the electrons contribute to opacity. That means kappa sub rho is 0 once we have a hot enough star stars. These are primordial stars, which are the first generation of stars after the Big Bang, because heavy elements need to be produced by stars. And once this is the first generation of stars, we don't have metals. So these population 3 stars could be objects by which we could test whether this dispersion relation has kappa sub rho equal to 0, and if we don't have metallicities and the stars are hot enough, so this means 0H main sequence population 3 stars are hot enough to have the complete helium and hydrogen ionized, and they do not have metals which could contribute. Professor Yadav was part of this study. This is a modal diagram for population 3 stars. You see the chemical composition: hydrogen 77, with a luminosity of log L over L sun 6.77. So what we see here is, so this star is should be affected by strange mode instability in any way, because find strange mode instabilities, but only below log TF 4.4. If we go to higher effective temperatures, there is no strange mode instability, which means, or which is caused by the fact that once the temperature is the is the uh, electron scattering, and we do not expect strange mode instabilities above log TF 4.4. To show you also the below log TF 4.4. These are the hydrogen and helium strange modes, but we do not have the iron strange modes because then the opacity is missing for the iron, and the opacity is in fact constant. Kappa sub rho is constant, and therefore we do calculations support the idea that the dispersion relation we have got here might be relevant for dispersion relation. This might be an ingredient for further studies of the instability. Well, to finish with that, we can use our findings that for ADI relation between pressure and density perturbation, which are out of phase by pi half. This means this an intuitive understanding may be gained that the restoring force in our wave, in our acoustic wave, is called increase the amplitude of a pendulum, then the force, the exciting force, should come in the right phase. Once the displacement of the pendulum is zero, you should have the biggest force. That means that the force is maximum when the displacement is minimum. So it has there should be a phase lag of 90 degrees. The ideal case for an instability to occur would be that pressure and density perturbation have a phase lag of pi halves. So we end up in that sense with the intuitive understanding, well, that we have an instability if the external force, which corresponds to pressure, the relation between pressure and density perturbation by the equation of energy transport. Okay, so finally let's summarize. Well, let's summarize our chapter on strange mode instabilities. Well, the limit of low gas pressure and low thermal timescale is given by omega squared is minus ikg times kappa sub rho. Kappa sub rho is necessary for this instability, and this is supported by our findings that in fact for POP 3 stars instabilities, at least in the initial phase in their initial phase of evolution, close to the 0 H main sequence. Okay, so these are the final statements concerning strange includes the group of yellow hypergiants. And with this recent study, we can then finally close this chapter of an unstable star. So thank you very much for today, and we'll meet tomorrow then to the final two lectures and sessions. Thanks.